So I kind of tease sometimes that this is just a really simple figure. Sometimes I put under my pillow to kind of remember things. Because all matter is made up of atoms, and atoms, as we know it by definition, must have mass and occupy space, so that's matter. But matter can be classified, kind of broken down. Matter can either be a pure substance or a mixture, okay? And if it's a pure substance, then matter has two choices. Matter can either be basically a lump of atoms that are all the same, okay, like a pile of copper, we call an element. Or it can be something like water, where it has two hydrogens and an oxygen, in a repeating unit. That's a compound. Okay, we'll be talking more about that coming up. Or you can have, and it's related just by kind of, if you have a salad, you have kind of an assortment of things in your salad, and nobody makes the tomato fuse into the lettuce. They just toss them together. So if somebody says, I have a chunk of matter and it's a mixture, then they have just physically tossed stuff together. The cool thing about just like a salad is you can separate them back out, your tomato and your lettuce and your onions, okay? And similarly, if you have a mixture like sugar water, okay, it's just physically combined. So you can undo that mixture back into its sugar and water components. Okay, so that's why we say they're related by physical means. The thing about the pure substances down here, you can go back and forth, or they're related by a reaction. So, and in here, you're not going to have to memorize, well, like how do I produce copper 2 sulfate? You're not going to have to know, like how do you do that, synthesize that. We'll talk more about chemical reactions later, but I'm sure you already have a sense of it that you can, I'm going to kind of emphasize what I mean down here. I usually do something like this. I say that you can take elements, ooh, gosh, spelling, elements, okay, and via a chemical reaction, and you've probably seen chemical reactions where they use an arrow to show that something's proceeding to form. So I'll just put chemical reaction. RXN is abbreviation for action. You can make compounds. Oops. I think we're all tired today. Or you can take compounds, and I've got a few animations coming up here. You can take compounds and break them back down into their individual elements, okay, using another different chemical reaction. And we'll be talking about chemical reactions later. Okay. So just to kind of emphasize this idea about having, there at the bottom of that that previous figure, there at the bottom of the previous figure, it had elements, compounds, and with regard to mixtures, it had homogeneous and heterogeneous mixture. So I'm going to kind of emphasize what those means. Elements, same color, same atom, okay? In this case, a pile of copper atoms. Sugar would look like this, the repeating unit. Okay, so, and these are examples of mixtures. Here we have tea, looks like tea, or might be coffee. I think I decided that might be a caffeine molecule. But here we have a mixture of 3 components. It's just physically combined. I love to think of those cute little water molecules, those cute little water molecules just swimming around. The sugar molecules swimming around. The caffeine molecules all swimming around. This is a mixture too, but as you probably know, that water and oil don't mix, okay? And they might mix just a tiny bit, but not very much. And that has to do with their, what we call polarity. But so this is a mixture too, because it's got 2 stuff, but they aren't mixed up, so it's a heterogeneous mixture. Okay, so just to kind of say it another way, in this class sometimes I feel like I say the same thing multiple ways, multiple slides. So you're just going to have to stay with it enough to say, oh, she said something different. But elements can be assembled to make compounds, okay? But if you have like a copper atom, there's no way that you can have an ordinary process other than a nuclear reaction to take that copper atom. You can't make it any smaller. Okay? Now there are that would be a nuclear fission, because fission is breaking apart and fusion is coming together. So you actually could, under certain conditions. So an element is as simple as it gets. Periodic table. We'll be talking more about the periodic table here. Okay. The different colors mean something. Actually, I'll go ahead and kind of give you a little preview. The yellow means that they are metals. It just says it up here. Okay. And the blue are nonmetals, and the kind of tannish oranges are kind of in between. We'll talk more about, this is my favorite, I call this, I don't know if it looks like it, but I call it a jag. All periodic tables have jags, and they separate the metals from the nonmetals, and along the jag are the kind of in-betweeners. Okay, so we'll spend some time talking about the elements, but each box is a different element. Okay. So picking on copper, kind of trying to get some close-up pictures of copper. Okay, even more of a close-up picture of copper. I'll try to animate this. I'm not sure it will animate for me this morning. But if it doesn't, that's okay. I think that means no. Okay. But let me just kind of describe what that last picture is. This is a close-up picture that we really can't take with a camera. Okay, but we know that this is basically what a typical atom looks like. And so those dot, dot, dots, what are those, you think? Would you say they're protons, neutrons, or electrons? What's the outside little particle?
Electrons.
Electrons. Very good. They're electrons. If you didn't know that, we'll get to it. Okay, but these little dot, dot, dots, let me pick on green. So dot, dot, dots are electrons. And for electrons, and again, I'm kind of getting ahead of myself, but all atoms have electrons, unless they're kind of strange. It can't happen. And we use an E with an upper negative. So what's in the center? The two things.
Protons and neutrons.
Protons and neutrons, exactly. Very good. Kind of reminds me of Christmas. So they're in the middle, and that's kind of the convention. So I'll put P plus for protons, okay, and N0, what's that for?
It's neutral.
Neutrons, yeah. So we'll be talking about the structure of an atom more, but that's kind of what, if you have a pile of copper atoms, they all look like that. They're kind of the repeating that, okay? Yeah. Element. Gotta love it. So here are some elements, okay, copper, carbon, cobalt, sodium, iron, potassium, different elements, different boxes on the periodic table. And just kind of some quick and simple stuff about the different elements. When it comes time to using a symbol, which is a letter, right? Like K is the symbol for potassium. It's always uppercase, okay? But if it's got two letters like calcium, it's uppercase C, a lowercase a. A good example of why you do that is this. So, for instance, what element? Well, it's already there. Okay, here's the symbol for cobalt. Okay, but what is capital C, capital O? It's a molecule. Carbon monoxide. Yeah, exactly. This is a molecule, and it means one carbon atom and one oxygen atom. Why? Because the O is capitalized. Okay, so it's kind of sloppy up there, but all right, some more pictures of atoms. When you guys were your gas water molecules in here, you were all walking around, and that's actually what's being tried to show here with helium in a balloon. All just like, ooh, okay. They have a lot of translational motion. Helium is an element. Okay, its symbol is H, capital H, lowercase e. Now, there are 7, I don't know how special they are, but there are 7 elements that always buddy up They don't like to float around by themselves. And that actually has to do with kind of how the electrons are around that atom. We'll talk more about that later. But there are 7 that like to be what we call diatomic. And a long time ago, I learned how do you remember those 7 by a German name, Hofbernickel. So if you spell out Hofbernickel, H-O-F, and the Bur part is Br. That's going to be the element bromine. Nickel, so Ni, and the Cl part is Cl for chlorine. Okay, so I have the symbol for 7 elements, Hofbernickel there. So what you're going to see, or you can already see on the next slide, is actually hydrogen runs around with another hydrogen atom. Okay, hydrogen runs around as what we call molecule, H2. Oxygen, same deal. O2. Fluorine doesn't like to be by itself, neither does bromine, nitrogen, iodine, or chlorine. So I put little subscript 2's there. Okay, so 7 diatomic elements. Very special. And this actually is the same list of the same 7, but this is increasing weight. Increasing weight. WT for weight. And here are the 7 on the periodic table. So here in a minute, we're going to kind of look at the water. Is water an element or a compound? It is a compound. Very good. That's the sort of thing that you might see on your test. Now, there are harder questions than that, and I kind of giggle, but that's okay. Let's see. So when you see water here in a minute, you're going to see that when it breaks apart, because water's got H2O, so how many hydrogens does it have? It has 2 hydrogens. How many oxygens does it have? 1, exactly. So H2O. So here in a minute, this is why when H2O breaks apart, okay, I'm going to do an arrow here to show it breaking apart to form something. What it breaks apart to form, you're always going to see it written as H2 because hydrogen is one of those diatomic elements, and O2. Sorry for kind of writing over that. Now, this isn't balanced, but I'm cool with this, okay? So oxygen, gotta love it. We gotta have it. But it's always buddied up. So when you see it written in an equation, you're going to see it like that. Okay. Some other pictures of elements, okay? Kind of showing you that element and their solid states sometimes kind of go together to make different shapes in the sulfur. So those are atoms all of the same type. So when you take atoms of different elements and combine them together, you end up with compounds. So water is a compound, you told me. What do you think is sodium chloride a compound or an element? It is a compound. Very good. Is zinc a compound or an element? It is an element. Exactly. So the fact that you have to have atoms stuck together, which happens with diatomic elements, but the fact that those atoms need to be different elements means that, like H2 or O2, that's not a compound. That's just so compounds have to have 2 different elements. I'm going to introduce you, that first bullet up there talks about that actually compounds can be classified as either a molecular compound or an ionic compound. And I'm going to kind of, it's not on your logic tree, that figure that I said, but I want to kind of introduce that idea. What they have in common is they have atoms that are stuck together in the repeating units. Okay, and you're going to write them just like you write the formula for H2O is H2O. You're going to write compounds like that. Okay, ionic and molecular compounds. So these are some examples of some compounds. Okay. So just to kind of get a visual, a water molecule would look like It looks like it has to have oxygen in the middle, doesn't it? I think I've already maybe drawn a water molecule. And then kind of at an angle are the two hydrogen atoms. It's definitely not linear. Carbon dioxide is linear. What do you think's in the middle for carbon dioxide? The carbon. The C, very good. So carbon in the middle, and actually it's got a couple of bonds to each oxygen, and it is linear. Ethane. It's got what we call a, and this is just kind of to make it more interesting or whatever, lecture interesting. But there's a lot of compounds out there that just have carbon and hydrogen. And so there's like a carbon skeleton and the hydrogens scatter around that. So here's my carbon skeleton, okay? Then I need to divvy up 6 hydrogens, and so it works pretty good. Each one of those dashes is going to have a hydrogen on the end. Okay, so that's ethane. And last but not least, we have calcium sulfate. Now again, you're like, well, maybe you do know how to name this calcium sulfate, but if you don't, we'll get to it, okay? Not this unit, but we will. So this is calcium sulfate, and this actually, of these that are listed, is kind of a special sort of compound. Have you heard of sulfate? Yeah. You've heard this sulfate, that sulfate, blah, blah, blah. Sulfate is an entity in and of itself. Calcium you probably recognize as an element. But they combine. So let me pick on sulfate. Anytime you see sulfate, okay, I mentioned it's kind of by itself. It's got the sulfur in the middle. And atoms are kind of, when you draw structures of compounds, a lot of times the atom ends up having like 4 things around it. Okay, it's kind of, so that's sulfate. And actually, I'm going to go ahead and say it's going to run around with I'll just leave it that way. So that's sulfate, and in this case, it just happens to have calcium attached to it. And we'll talk more about this, but let me go ahead and connect the calcium to my SO4, and instead of a straight line, I am going to do a dashed line. And let me draw a circle around the full CaSO4. So that's just kind of an introduction to what calcium sulfate looks like. So these are all compounds. Those would be the repeating unit you'd see if you looked at those molecules or formula units. So all this one is saying is, a minute ago when I asked you about water, okay, when I asked you about water, what I was after was that there are 2 hydrogens and 1 oxygen. So that's all this is talking about. H2O. There's no number next to the oxygen, but so it's implied that it's 1. All right, so here we go again. This is, you guys don't have this one, right? Okay. But just to kind of emphasize, up here at the top, I'm going to just say that we could take 2 or more substances, pure substances, and simply toss them together, tossed together, to make a mixture. They're just physically tossed. Okay? And we can actually then physically separate them back out into their individual substances. And then just we could go from elements to compounds, or compounds, break them back down to their elements using what?
Chemical reaction.
Yep, a chemical reaction, exactly. RXN is reaction. So we're going to kind of look at the taking a compound and breaking it down into its elements. Okay? And a lot of times, you know how that arrow, that whole arrow thing I've been drawing, like something starts like this, I draw an arrow and ends like this. A lot of times, whatever you apply, like if you do apply heat, or if you do apply electricity, they'll just kind of shorthand notation, put it over the arrow. It's kind of like, yeah, that makes sense. I think scientists like to be few words as possible. which I can appreciate. Okay, so let's take a look at, this is mercury 2 oxide breaking apart using flame. Okay. The next one has a video too. Let me just go ahead and play that video for you. I think that's already queued up, so that's a good thing. Okay, I think that's it for a little bit. Let's see what else we got. Okay. So I mentioned that I just want to kind of introduce you to the idea that if somebody gives you a compound and they're going to use a formula, a chemical formula like H2O to tell you what that compound is. Actually, compounds come into two broad categories. That formula either represents a compound that is what we call a molecular compound, or it represents a formula of a compound that's an ionic compound. And we'll be talking more about that because we're going to spend some time talking about the nature of how atoms stick together to make compounds in the first place. Okay? But one of the things is that if it is a molecular compound and you have a repeating unit, a cute little, okay, you have a molecule. Okay? If it's an ionic compound and you have a repeating unit, then you have something called a formula unit, abbreviated FU. It really is. I think that's funny. Okay. I'll go ahead and tell you, and I think I have it coming up, but everyday examples of these two types of compounds. When you guys were water bits, okay, repeating units of water, you actually were molecules. Okay. So an example of a molecular compound is H2O. Okay. An example of a compound that we all appreciate, especially at the dinner table, is table salt. What is the formula for table salt? What do you think? NaCl. It is. Very good. Okay, so NaCl is an example of an ionic compound. Okay. So if you have a repeating unit of table salt, then you have a formula unit. Okay. So bringing this up one more time, and you might have to go back. Under compounds, I'm going to add to the structure, and just based upon what I just now said, I'm going to say compounds can either be molecular compounds. CPD is my abbreviation for compounds, or ionic compounds. And if it's a molecular compound, your repeating unit is a molecule. And if it's an ionic compound, what's your repeating unit? It is a formula unit. I think that's the history of rock and roll. Okay. So again, I'm just getting a little bit kind of presenting the idea to you. We'll dive into it more, but I wanted to just say a little bit more about these two types of compounds. So the deal with a water molecule then is that it has no extended family. It is just its own little family, its own little nucleus family, okay? So that's to say that for every 3 atoms stuck together, it is a specific oxygen with 2 specific hydrogens. That's it, okay? So actually, water, H2O, methane, cows do it, has a central carbon atom and 4 hydrogen atoms around it, is a molecule, and ammonia, NH3. Now those, of course the white balls in NH3 are hydrogen atoms. Those little dots there that are kind of hovering over the nitrogen atom, those actually are 2 electrons that are associated with NH3 also. They're what we call lone pair electrons. We'll talk more about that later. But aren't they adorable? They're invisible, but they're very important. Okay. Okay, so just kind of showing you the pretty fountain with the liquid water coming out. And so kind of a blow up of the repeating H2O molecules. Don't they look like Mickey Mouse with the... This actually mentions the word water. You just assume it's water. Well, we know that unless you pay a lot for it or using it in a very fancy experiment, probably your water has some other cool stuff in it. In the chemistry lab, we actually prepare, we run water through a type of filter, so we try to remove ions. And we have some reagent grade water in the chem lab. So if I don't say anything, remind me to tell you where is the good water that you need to use for your experiments. So, all right. So ionic compounds, okay, if you have a repeating unit of table salt, that is NaCl. Well, it would be one sodium and one chlorine, but we would call that a formula unit, not a molecule. So, I think we'll got these down here. This one first. All right. Oh, one more. I think that'll do. Okay, so this is just a still image from your textbook to kind of show you the alternating colors. The alternating orbs means they're different atoms, okay, in a crystalline lattice structure. There's a whole study of science called crystallography that looks at kind of the different facets that are formed. Okay, so if you, in the figure we saw, the thing is you can circle a sodium and you can circle chlorine, but if you look closely, it's actually attached to 5 other sodiums or 5 other chlorines. So you're like, which pair do I circle? So, all right. So we got to the assignment slide. Let's take a look at what these are. I have the e-textbook version. That's not you guys. Come on. They're not too bad again. So 31 and 32. You're supposed to say if it's a pure substance, classify, okay. In 31, they are all pure substances. You're supposed to say if it's an element or compound, so it shouldn't take you too long. And 32, I think similarly. They are pure substance, and you just have to say if it is a element or compound. Not too bad. Any questions? And that's all. I think we'll stop there today because I didn't print out more. But I'll print out a few copies. How many people still don't have their notes? Okay, hopefully, like I said, we'll see what today brings, but they're supposed to be over there. Okay. Have a great weekend.